Great, thank you for the introduction. Thank you especially for organizing this conference, and thank you all for your attention and for attending the talk. So just as an outline, we're going to talk about basically two separate papers that have a lot of themes in common. One is going to be in the setting of Calder-Sigmund operators, much like the previous two talks of this parallel session. And the second is going to be concerning Toeplitz operators on the Bergman space. Okay, so just as the last few talks, we're going to be considering first Calder-Sigmund operators. So these are given by, we have to assume a priori that they're bounded on, say, L2. And formally, they're going to be given by integration against some kernel function. And this kernel function is going to have a singularity, so it's going to be defined away from the diagonal, but it has some size and smoothness properties that sort of save it and allow for us to get some properties that we want. This is a general framework kind of introduced by Calder-Sigmund in the 50s, and some motivating examples are the Hilbert transform and the Riesz transforms, which are given by these two formulas. So you can see exactly what the kernels are, this with some appropriate scaling constant. And for the Riesz transforms in higher dimension, we get this. The Riesz transforms collapse to the Hilbert transform when you're in dimension n equals 1. Okay, so the main properties of Calder-Sigmund operators that we will care about in this talk are that they're LP boundedness for p's that are between 1 and infinity, exclusive, and at the p equals 1 endpoint, this property fails, but instead we have the weak L1 estimate. So weak L1 estimate. So it's going to map L1 into the weak type space L1 infinity, just like Maria Jesus was talking about in her talk, these weak type estimates. Okay, and just to remind ourselves what these definitions actually are, LP is the space of functions that are p integral raised to the pth power, and that integral needs to be finite. And the norm is given by taking the 1 over p power of that. And the weak L1 norm is given by this supremum over this quantity involving the distribution function. The main question in the theory of weighted norm inequalities is how do these properties extend to more general measure spaces? So these spaces here are defined. So our operator is defined as integration with respect to Lebesgue measure. And the properties here, the classical ones, are boundedness properties on spaces that are also with respect to Lebesgue measure. The question is, can we tweak this measure here? And this is denoting the Lebesgue measure of this distribution function of this level set. Can we tweak these measures and still get these boundedness properties? So in particular, we're considering weighted inequalities where we have an absolutely continuous positive measure given by this locally integrable function W. And we're introducing the weight here. So this weight for the weak type estimate, that's your weighted measure given by integration against W. Okay, so that's the main question. For which weights are our specific operators that we're looking at? For which weights are they going to possess their weighted boundedness properties? And that's kind of the main theme of my direction of research at the moment, is given just any operator that we know has boundedness properties, for which weights is that going to hold? So for the Hilbert transform, this is a classical result of Hunt, Muckenhout, and Whedon, that the Hilbert transform is going to extend boundedly on the weighted LP spaces if and only if the weight W satisfies the Muckenhout AP condition, which we've seen a few times now. It's given by this supremum over this product of averages being finite. So this is my notation for average. I use these angled brackets, and that's the integral average of our weight. P prime is the Holder conjugate exponent. And here we're taking a supremum over all, I guess in higher dimensions, Q stands for a cube, but the Hilbert transform is a one-dimensional object. So that's the cubes are going to be intervals. And also characterizing the weighted weak type 1,1 boundedness, we have an A1 condition, which we just have to reinterpret the second factor of the product that we're taking our supremum over, because in that case, P equals 1, so P prime is an infinity. So what the heck does this even mean? Well, we reinterpret it in this way. We take the L infinity norm on the cube of our reciprocal of our weight. Okay, so that exactly answers the question for the special case of the Hilbert transform in general. Just like John Oliver was talking about in his talk, the AP condition is going to be sufficient, and A1 for the weighted weak type 1,1 property, and it's going to be necessary for the non-degenerate Calder-Sigmund operators. So this is the correct class to look at when we're studying the generality of all Calder-Sigmund operators. Just to mention some things that were discussed earlier, I mean, there's more classical proofs, but the hot area of investigating this is using sparse operators, and you can get optimal dependence using this. So we're going to be looking at a subclass of Calder-Ziegman operators, those that actually act compactly on our Lebesgue spaces. So all the Calder-Ziegman operators by definition, by assumption, are going to be bounded. Now we want to improve that property to compactness. Remember, compactness is going to be a stronger property than boundedness of our operators. So maybe some Calder-Ziegman operators act compactly, and we want to understand which ones do that. This was first characterized by Villarroya in 2015, and he gave a T of 1 type theorem for compactness of Calder-Ziegman operators, and then proved that if it's going to be compact on one LP space, then it's going to be compact on all of the LP spaces between 1 and infinity. And in joint work with Villarroya and Olson, or I mean, not me, but Villarroya and Olson did this in a separate paper where they addressed the endpoint, and you also get the appropriate formulation of compactness there. So what we did, the first result that I want to present, and I don't want to dwell on this too much because it's sort of technical, and I want to go into a different setting where I can describe the ideas a little bit more easily. This paper of myself and Villarroya and Brett Wick, we discussed the weighted theory for compact Calder-Ziegman operators. So our main result here, the one that's easiest to state, is that if you have a compact Calder-Ziegman operator, so one of these nice Calder-Ziegman operators, then it's actually going to extend compactly for any weighted space where the weight belongs to AP. We achieve this by establishing an appropriate sparse domination result for such an operator. And our sparse domination, and this looks a little bit more technical, but it is stated as the following. So if we take one of these compact Calder-Ziegman operators, we can subtract some finite rank paraproducts and get this finite rank perturbation of it. So that's what this tilde is saying. We subtracted off the paraproducts to get the necessary cancellation that we need. And then we're taking the projection operator onto a tail of our space, and this projection composed with our cancellative Calder-Ziegman operator can be dominated above by this finite sum. So we have a finite sum, just 3 to the n, of sparse operators that are just these averaging operators. And importantly, we have this coefficient of epsilon out front. So this epsilon here is our small quantity, and that's what's going to allow us to achieve our compactness result. We want to basically bound the norm of this projection, the norm of this projection composed with our Calder-Ziegman operator. We want to bound this norm arbitrarily small times the norm of f, and this sparse domination is what allows us to do that, because we have this our small epsilon out front. Okay, in the same paper, we also discussed a model case of Haar multipliers with martingale transforms, the diagonal setting, and there the results are a little bit cleaner to state, which I would have liked to discuss here, but the fact that we don't have that much time, I'm going to discuss a different setting, which very much looks like our Haar multiplier setting, and that's the setting of Toeplitz operators on the Bergman space. So we're sort of shifting gears here. Now we're going to a more complex analytic setting. So we're going to be working on the Bergman space of the unit ball in Cn. This is the collection of all square integrable functions that are also holomorphic on the ball. The operator and the sort of the analog of the Calder-Ziegman, the standard Calder-Ziegman operators in this setting is the Bergman projection. So one can show that the Bergman space is a closed subspace of the L2 functions on the ball. So there's going to be an orthogonal projection operator, and it's going to be called the Bergman projection, and it's given by this integral representation where K of ZW is the reproducing kernel for the Bergman space on the ball. So this, by analogy, looks a lot like a Calder-Ziegman operator. And actually, it does have a lot of the same properties, because in this case of the ball, we have an explicit formula for this reproducing kernel. It's given by this expression here, which again is going to be singular on the boundary diagonal. So here the problems are on the boundary of the ball. So just like how the Calder-Ziegman operators, just by analogy, those are singular on the diagonal in Rn. This is going to be singular on the boundary diagonal of the unit ball in Cn. To understand compactness, we consider Toeplitz operators, which is just you pre-compose the Bergman projection with a multiplication operator corresponding to some symbol function u. So you take a function u on the ball, you first multiply your input by u, and then you take the Bergman projection. Doing this as an integral operator, it's basically just perturbing the kernel by your symbol function u. So this, in comparison, is more along the lines of the compact Calderon-Zygmunt operators. If u possesses decay, then that's going to feed into decay of this kernel, and we can expect better properties of the Toeplitz operator over the Bergman projection itself. Okay, so there's two motivating results here that are analogous to the weighted results of Hunt, Muckenhout, and Whedon for the Hilbert transform, and also another result that's analogous to Villeroy's characterization of compact Calderon-Zygmunt operators. In this setting, Bekele, extended work of Bekele and Bonamy, in the 80s, characterized the weighted bounds for the Bergman projection itself. So the Bergman projection P is bounded on weighted LP spaces. Here I'm using sigma instead of W because I don't want us to get confused with complex numbers W. So I'm using sigma for the weight in this setting. But the Bergman projection is going to be bounded if and only if this BP condition, so we're switching from A's to B's in this case. So we call this the Bekele-Bonamy condition. Holds, where we take the supremum of the product of these averages of our weight. Again, this is the same sort of formulation as what happens in Muckenhout's AP condition. The difference here is that we're taking the supremum over these TZs, which are Carlson tents. So the Carlson tents are objects that are not exactly cubes, but if this is the unit ball in one dimension, so it's the unit disk, and here's a point Z in the unit disk, the Carlson tent is going to look something like this. So it's some sort of object that passes through Z and intersects the boundary. The point is these objects all intersect the boundary, which may be expected because that's where the bad behavior of our kernel is. The Bergman kernel is singular on the boundary diagonal, so it sort of makes sense that the collection of objects that we're defining our weight condition by is related to the boundary. And likewise for the weak L1 inequality to hold, or this Bergman operator, the same type of condition holds as with the Muckenhout's A1 condition, but again, we take a supremum over these tents instead of all cubes. Okay, so that's the main motivating weighted norm inequality type result to our work. And for the compactness, we can understand exactly, so if U is an L infinity function on the ball, just bounded function, then clearly TU is going to be a bounded operator on LP because you can just apply the boundedness of the projection and then pull out the L infinity norm of the symbol U. But the interesting case, if you have an L infinity symbol that maybe possesses more decay, then you can expect better properties. And the question is, when is your Toeplitz operator going to be compact? This was solved, I don't credit this to Axler and Zhang, but there's a bunch of papers on this. They solved this first in the case of the unit disk, and they characterized the compactness of the Toeplitz operators by the vanishing of the Berezin transform. So the Berezin transform is given by the A2 inner product of the Toeplitz operator applied to a normalized reproducing kernel, inner product with a normalized reproducing kernel. If that vanishes, that exactly characterizes the compact Toeplitz operators. So in this setting, these are our two main motivating results. We have the weighted theory for the Bergman projection. We have the unweighted compactness theory for the Toeplitz operators. We want to connect these two and understand the weighted theory for Toeplitz operators. So there's two types of results that we have in this newer paper. The first line is about weighted compactness results, so extending Axler and Zhang type results, but in weighted settings. And another one, interestingly, is, or my opinion, interestingly, is extending the weighted theory for Toeplitz operators. So again, the idea is that if you have decay on your symbol U, then you can expect better operator theoretic properties of TU. And one way you can improve the weighted properties is maybe you get weighted norm inequalities for weights in a larger class than just this BP class. So we want to describe a U-adapted class of weights for which the Toeplitz operators would act boundedly. And we sort of achieve this, or we do achieve this in a way. Okay, so our first result here, which I'm a lot of pauses, I'm just going to show the full slide, is a sufficient condition for the weighted compactness for all Becquerel-Bonamy BP weights. So our first result is if U itself vanishes as you go to the boundary, then TU is going to be compact on the weighted LP spaces for every single Becquerel-Bonamy weight, and likewise at the weak type endpoint. So to prove this, we developed some Riesz-Kolmogorov type characterizations of the pre-compact subsets of the Bergman spaces, the weighted Bergman spaces. And we can actually, in certain situations, relate our assumption back to the Berzin transform condition. I mean, this here is a sort of strong condition, right? We're assuming that the weight itself vanishes. But the Berzin transform is a weaker condition to assume because I can like detect oscillations. If your symbol oscillates very quickly, that can still vanish as well. But in the case of you have a continuous symbol, then the compactness is going to be characterized exactly by the Berzin transform. Again, this is sort of assuming a lot on a symbol that's continuous towards continuous up the boundary. So can we get a more general result for any L infinity symbol? And that's kind of the spirit of our second compactness result, which to state, I first need to talk about a dyadic structure on the unit ball. So here's some technical things, but I'm just going to go through and then state the idea. So basically what we're doing in one dimension, we have the unit ball, which is just the disk, and we're going to introduce a dyadic structure on it. So we're going to start with just some core, and then you develop these annular shells. And each one of these little objects that I'm describing, trying to draw here, is called a cube. We call them cubes with a K because they're not exactly geometric cubes, but they play the same role of dyadic cubes in the dyadic situation. But the point is we can take the ball and partition it in a way where we have properties that are akin to the dyadic system on Rn. And the tents in this situation are comparable to the Carlson tents. Therefore, we can develop a dyadic BP weight condition that is going to be equivalent to our BP weight condition that involves Carlson tents. So basically, we're just turning this into a dyadic problem. Using this dyadic problem, we can assume a little bit more about our weight where we have a reverse Holder condition. So this is the same thing as what we would have with the reverse Holder condition for Muckenhat weights, which is automatic for A infinity weights. In this case, it turns out that BP weights need not satisfy a reverse Holder inequality. So we're going to assume that. And if we assume the reverse Holder inequality, then we can characterize the weighted compactness of Toeplitz operators exactly by the Berzin transform. So the Berzin transform vanishes if and only if your Toeplitz operator is going to extend compactly on the weighted LP space or weighted Bergman space AP. But for this, we need our weight to be Becquerel-Bonamy and also satisfy a reverse Holder inequality for the proof to run. And that's because the proof follows from this extrapolation of compactness argument, which was a recent result of Hooten and Lapis. But they did this for Muckenhat weights, and we redeveloped we adapted their argument in the setting of Becquerel-Bonamy weights. So basically what this is saying is that if you have bounded, so P0 is some fixed exponent, maybe think P0 is 2. If you know that you're bounded for all of the weights at that fixed exponent, and you're compact just at some weight, typically in applications, you would take this to be just the constant function sigma 0 equals 1, so the unweighted case. So if you're bounded for all of the weights and you're compact just for one of the weights, then you're going to be compact for every single exponent for all P between 1 and infinity, and for all appropriate weights. Again, we need to assume some reverse Holder conditions on our weights and the dual weights for the argument to run. But this is what we have here, this extrapolation of compactness. If you're bounded for all weights at one exponent and you're compact for some weight at that exponent, then you're going to be compact at all exponents and all weights. And this is going to easily imply our Axel-Rajang type theorem. Okay, now I know I'm almost out of time. I apologize for taking maybe one more minute over my time, but I want to discuss these results here, which is an improvement of Toeplitz operators over the Bergman projection, but in terms of the classes of weights on which they act boundedly. So we're going to define this new class of weights, which we call UBP, because it's going to be dependent on our symbol function U, where we take just our normal BP condition, but we also introduce these coefficients, the L infinity norm of U on our dyadic tents, and likewise for the UB1 case. The idea here is if our symbol function U will decay towards the boundary, meaning we can encode that by these L infinity norms going to 0 for some sequence of tents, which would go towards the boundary. Then this would go to 0, which would allow these products to go to infinity. So therefore, we could have weights that are not necessarily in BP, but would be in some UBP class where U is going to have decay. Our techniques for the theorem that I'm going to state on the next slide are a sparse domination, which is just an adaptation. It's basically just estimating the kernel of the Bergman projection, but you can get effectively a sparse bound here. So you sum up over your dyadic system, you have some averages, and multiply by the characteristic function of your tents. That's the analog of our sparse operator. And with this, we can get the following result. If you have a weight that is in U to an appropriate power BP, so this is going to be a class of weights that is larger than BP, then your Toeplitz operator is going to be bounded on LP of sigma. And you can get this, since we're using sparse operators, you can get the exponent that is analogous to the sharp exponent for the Bergman projection, for Calder-Zygmunt operators in general, and so forth. That's just in word summary, summarizing what the result is really saying. And then likewise, we can get a result for weights that are beyond the B1 at the weighted weak type 1,1 endpoint. So if you have a weight that is in UB1, which again is going to extend beyond the B1, here our arguments are going to also rely on a reverse Holder condition. So we're going to assume that, and we can get this quantitative bound for our Toeplitz operators on these weighted spaces, which again is going beyond the B1. So this is not necessarily going to hold for the Bergman projection, but if our symbol U decays, then we can get weighted boundedness here. And I'm out of time, so I'm not going to go in detail with our next results, but this is basically saying that the reverse Holder class is not empty. There's a recent paper of Alleman, Pot, and Regera, where they studied this B infinity and the reverse Holder for BP weights. And they considered this class of weights here, where the weights are more or less constant on like the interior of your ball. So on the dyadic cubes themselves, not the tents, but the cubes. So you have some irregularity. Our results that involve the reverse Holder assumption will have a corollary when applied to these weights. Instead of assuming reverse Holder, we're saying that our weights satisfy that irregularity condition. Satisfying one. The quantitative bounds get a little bit different. And then the last result I want to say is if you take this result here and you just replace U equals to 1, then you're back to the situation of the Bergman projection. And in that case, we get a new improved quantitative result for these weights that satisfy this irregularity condition. I just want to end with that. So this is a theorem taking U equals 1, then we're back in the situation of the Bergman projection. If we have a B1 weight that satisfies this irregularity condition, then we can get a quantitative norm estimate for the weighted weak type 1,1 norm of the Bergman operator by this, which improves what was previously known for this class of weights. Looking through the literature, the only weighted weak 1,1 estimates are given in Beckley's original paper and a paper of, again, myself and Wagner, where we do this in a general domain setting, a more general setting, where if you look at the proofs, you can only at most get a B1 squared, where in this case, if you look at this class of weights, where C sigma remains bounded, then you have a B1 times the log of B infinity, which is analogous to the optimal quantitative estimate for Calder-Zygmunt operators. If we consider these radial weights, that's an appropriate class of weights to look at and see this optimality. Okay, I'll end here. Sorry for going over, but thank you for your attention. And yes, thank you.